So in this video, we'll talk about temperature and pressure and how we can shift an equilibrium by changing those stresses. Uh, feel free to stop the video, pause if you need to write something down, or wait till after to look at the slides and copy them from there. But do try and do both things at once. So, temperature. If I'm going to change temperature in an equilibrium, what does that look like? How does that affect it? How can that change an equilibrium? Well, let's just look at this real quick and think about what I was saying at the end of the last video. When a bond is formed, energy is released. When a bond is broken, energy is absorbed. So if I were to just show this to you, and I know all of you know this, if I was to just show you this, and I would say, is this exothermic or endothermic? Well, you would say, duh, Mirage, we're forming a compound, and when a bond is formed, energy is released, so it's exothermic, and we would write energy over there. But try and read it backwards too, right? What's happening is I go backwards through this equation. I'm taking a compound and I'm breaking it into its elemental components. When a bond is broken, energy is absorbed. So in this reverse reaction, there's an endothermic situation at hand. Energy absorbed. I'm using this and this to go backwards and make this and this. Okay, it's good to know that. So temperature. What happens when I change it? How do I look at it from a equilibrium standpoint? Well, I want you to treat it like a molecule. Like treat it like what we just did, changing the concentration. Right? If I increased, from the last video, if I increased N2, that created more collisions, and more collisions shifted this to the right. Now, these are just notes that you can have. I don't really refer to this much because I refer to it in my my own way. But when you increase heat, you're going to favor the endothermic side, the side without energy. And when I decrease, we're going to favor the exothermic side, the side with energy. And when I say favor, I'm talking about the side that is going to be created. So thinking about it from here, if I increase heat, energy is right here. If I increase the heat, I'm going to have more energy. More energy in the system is going to break more of these molecules apart. And thus, more reactants are created. If I decrease the energy, if I took this energy away, the system would get cold. And every equilibrium, think about it. If it gets cold, it needs to correct that. And so it needs to make more energy. And the only way to make energy here is to do what we call as a shift to the right and make it. I'll stress again. Wherever we're shifting is the side that's being created. So if I remove the energy, I will shift to the right so that I can create more of that energy. It's a balancing act. It's a seesaw. When something goes wrong, we need to correct it and either add it back or take some of the new stuff away. So let's look at it from this standpoint. Right? What would happen if energy was to increase? Here's energy. Right? If I had a sudden increase in energy, some of you already know what's going to happen because you've been paying attention. But if I increase the energy, what happens? Is it going to shift to the left or is it going to shift to the right? Take a second, think about it. It's going to shift to the left. And whenever I shift to the left, my reactants then increase in concentration. N2 and H2 are now being formed. Great, good, sure. What happens if energy is decreased? Well, the opposite happens. we're going to shift to the right. And I said it because if it gets cold, the equilibrium freaks out and says, I'm cold. I got to do something about that. So let me just make the energy. And the only way to make energy is to push this equation that way. I think I told some of you this story, but I'll tell you anyway. It's about this equation, and it's about the man Le Chatelier. So Le Chatelier went out for, I don't know what, but he went out to get coffee one day from his lab while he was using this reaction, right? And he left his lab assistant in charge. And he told his lab assistant, make sure that you decrease the temperature, right? Decrease the temperature, and make sure you add some more hydrogen into the situation. And so what happened when he did this, right, is the increase in the reactant pushed the equilibrium to the right. More hydrogen was colliding with nitrogen, and it pushed it to the right. The decrease in temperature made the reaction push even further to the right because now there was a lack of energy. So now the equilibrium was shifting right for two reasons. There was more hydrogen in there, and there was less energy. So the equilibrium was saying, I need to make more energy. I need to make more energy. I have a lot of reactants. I need to make more products. I need to make more products. And as a result of this super shift to the right, a lot of energy was produced. And it blew up the lab, and his lab assistant, well, he didn't make it out in time. So, and that's a true story. Fact check that. Go for it. Go for it. All right, so that's temperature. We're going to work with that. We're going to work with it. We're going to work with it. Pressure is the last thing that we are going to change. And oh my goodness gracious, I bet you could have guessed it. It only affects gases. All right, I'm going to try and explain this as simply as possible because I don't want to confuse you. That's the last thing I want to do right now. But we have to be looking at the total moles. Total moles of gas. An increase in pressure favors the side with less total moles. And so one of the first things that you should do whenever you get a question like this is to say, all right, how many moles of gas do I have? You know I like the line down the middle, so I split it and I say, well, there's 1 mole of gas here, there's 3 moles of gas here, 4 total moles of gas on the left side of the equation. This is 2 total moles of gas on the right side of the equation. So if I were to increase the pressure for this equation, this changes every time, but if I were to increase the pressure, this equilibrium here would be favored on the right side, and we would see a shift to the right for this one. It's basically because there's less space, right? If I were to say there's an adult and a toddler in a room, and one of them had to play hide and seek and hide in a small tiny box, the smaller person, the smaller amount of moles is going to fit more snugly anyway in that smaller confined space. And that's what you got to think about, right? Increase pressure, decrease volume. 2 moles is a lot smaller than 4. All right. If I decrease, obviously the opposite would happen. There'd be a lot more space to move around. So this equilibrium would shift to the left. A lot more room to spread out. So let's use more moles to do that. Alleviate the pressure. There's no shift if the moles were equal. Look out for that trick because that comes up. You know how the Regents likes to throw these little tiny nuggets in there. But if each side of the equation had the same number of gas molecules, there would be no effect. Also, there's no effect if no effect for solids and liquids. All right. So we already covered it, but I'll just go through it one more time. If the pressure were increased here, we would have a shift to the right. And we're shifting to the right because there are fewer moles on the right. So there's less moles for the small amount of space that's going to be there. So we're going to shift that way. You can also think about it because if the pressure is being increased, we're almost forcing these molecules to bang into each other. And when they bang into each other, they create this product. Back to that original kinetics that we talked about. If we decrease the pressure, we're going to shift to the left. When we shift to the left, concentration of nitrogen goes up, concentration of hydrogen goes up, and we're using the NH3 to do that, so it decreases. Okay? And there are more moles on the left. Yeah, so I do understand that is a very difficult concept to grasp, and I am sympathetic to that. So we're going to take a little bit of time to do this. I'm going to show you a trick in the next episode, I guess you would call it, where we will be looking at equations and we're going to be predicting how one set of criteria affects the entire equation. So hopefully by the practice piece, we'll be okay. I'd like to believe that. But we got to do the best with what we can. And as long as you're really putting a good effort into this, you'll be rewarded in one, you may not see the rewards right now, but it will have a long-lasting impact on how you learn in the future, whether that's in college or in your career. This is a really important skill that a lot of you guys are taking and running with, and that's learning how to be diligent, manage your time, and take things seriously. And I really do commend all of you because we are seeing some seriously high percentages of work completion. And I don't want you to get discouraged, but I want you to just keep doing what you're doing and keep putting in that effort. And honestly, like I said, it will pay off. All right, I'm going to stop rambling so that we can get to this video and we can feel a little bit better about that. All right, great. Good talk.